1000的错，太给了，给了。这你好受不了呀！
对啊，
请启出话筒。
啊，对。Okay, before we start, there's some correction here. So we have this TFAE statement for Excel choice, but we didn't prove it. And I have a correction here that is for Hausdorff maximum principle, right? Any partially ordered set contains a maximum chain, not element. If it is elements, right, then we are kind of like simplifying Zone's lemma already. Okay, without the upper bound property, we already have elements. So it's a chain. Sorry, it's a chain here. So what's a chain? So a chain in a ordered set is a totally ordered subset. Okay, this is what we call a chain. Because if you are totally ordered, you know how to compare every two of them. So you can arrange them in a chain. And then what's the maximal chain here? So a chain is maximal if there's no other chain in X which has T as a proper subset. Okay. Okay, it's like a maximal ideal like that. Okay. So maximal chain. Maximal chain. Yeah. And this for TFAE, right? Not all the implications are very hard. Okay. Some are not as hard as the other. Okay, so you can try and do some of them if you like. But some are really hard. Okay, some implications are really hard. Okay, so I won't test you on this. But it's better you have an idea that these are the same thing. Okay, in particular, this and Zamenhof well ordering principle here says that any set admits a well order. Okay, so if you think about for example Z, okay, for example Z integer, okay. So if you look at integer, you look at any subset of the integer, it's not always you can find the smallest number. For example, you just look at the even integer. Okay, it's -2 the smallest. You still got -4, right? Is the -4 still smallest? Okay, you cannot find the smallest one. But this Zamenhof well ordering principle says that if you change the ordering, okay, on Z, you could get well orderedness. Okay, you can find the smallest element in every subset. Okay, no matter internal or finite. Okay, no. Yeah, but how to do it? You need axiom of choice to help you to do it. Another thing I want to update on axiom of choice. So, well, last time I gave you an analogy that I have four pencil cases, right? Okay, you have 4 pencil cases. So let's say these 4 pencil cases have 2 pencil in each of them. So well, I think use your intuition, right? You think that it's easy to pick one of them out, right? It's easy to pick, you can pick it. Okay. And another case is what if I have infinitely many pencil inside here? Infinitely many. Can you still pick or not? Can. I think you still can do it, right? Since you already can pick for finite cases, you also can pick for infinite cases. But what is really about axiom of choice is, can you do infinitely many choices or not? Okay. Collection of non-empty set. I didn't say how many of them. Can you do infinitely many times? 你可以做无限的选择吗？可以哦。哇哦，你没有看过戏咩？我没有选择哦，这次我这次没有选择，I have no choice。啊，他是人类，这次我没有选择哦。OK，SL choice say that you have choice，就是你有选择的。Yeah，you have choice. It's just that you want to make it or not. Okay. 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 So this is the axiom of choice. In particular, when you use it to define the right inverse of an onto function. Okay, right inverse of an onto function, because you don't know how many choice you need to make. Huh? Sorry. Yeah. Z. What do you mean Z? 用什么？用在哪里？if I okay for assignments, right? If I ask you to prove some statement that's already stated in lecture notes, right? You have to prove it. Okay, you cannot use. No, it's the same statement. How to use? Proof in lecture. You know, like that, right? Obviously, when I ask the exact same question, I want you to do it. Huh? Use the axiom of choice? Yeah. Yeah, just use the axiom of choice. Yeah. But you cannot say that, oh, this is proven in lecture, so it's true. Not like that. Okay, yeah. Okay. Okay, now. All right. Let's continue. Yeah, let's continue. Okay, so last time we are in cardinality, and then we proved that rational number is enumerable. Okay, let's continue with some theorem here. So let's say x is infinite, then S will contain a enumerable subset. Okay, so let's recall first what does infinite means here. Joshua, what does infinite set means here? What's the definition of infinite set? What's the infinite number of elements? Sorry? What's the upper bound here? Do you have order here? Before introducing infinite, we introduce one concept, which is ordering is very front already. Before infinite, we count, right? You need to count, right? Counting is finite. Usually it's finite. Okay. So infinite is just mean not finite. That's all. Okay. What does finite means? What does the set is finite means? Sorry? What? 没有，听不到。Equivalent to n. So what does equivalent to n means? Equivalent to what n? Natural number n. What does that mean? Bijection with n. N got how many things? Infinite. What is a finite set means? 郑业 what does a finite set mean? 不要想要这样复杂这个是很正常的一个很正常的一个想法就是有些嘛，哎，啊哈，what say again? What is a finite set? So you can form a bijection with the set containing 1, 2, 3 up to n. OK， 对吗？bijection 1、2、3、4、5、6、7、8，好，8个咯。You form a bijection with number 8. Okay or not? Yeah, it's very natural. These things are very natural, although we write it quite formally, but it's very natural one. Okay. So how to create a denumerable subset here? So denumerable set is what DDR say, right? The set is equivalent to n. Okay, so how do you form a denumerable subset here? How to form denumerable subset? Is this set empty or not? If it's empty, it's finite, right? So it's not empty. Okay. So since S is not empty, what can we do here? We can take an element from S. Okay. And then can we pick a second element or not? Why? Since S is not finite, S cannot just contain S1. Okay. So there exists S2 in S such that S2 is not equals to S1. Okay. Similarly, you can find S2 in S such that S3 in S such that S3 is not equals to S2 and S3 is not equals to S1. Okay. And then we can see that this process here will never stop. Okay, will never terminate. Otherwise, if it stops, right, what happens? You just have finitely many elements inside there. Okay. So if you keep continue on, we can construct a denumerable set. Okay. Do we need axiom of choice here? Where we use axiom of choice? When we try and pick all these Si. Okay, actually we use the axiom of choice here because we are doing infinitely many choices. Why can you pick it? Okay. Okay, the set we are considering for axiom of choice here are X throw where X1, S throw where S1, S2, S throw where S1, S2, S3, and then keep on. Okay. So there are infinitely many choices here. Use axiom of choice. Okay. Okay now. Okay. Okay. Continue. Next proposition. A countable union of a countable set is countable. Okay, so what does this mean here? So if A1, A2, blah, 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 is a sequence of countable set, so each of them is equivalent to a countable set. So countable means what? Either it is finite or denumerable. Okay. Then the union of all these AI is also countable. Okay. Last time, how do we prove countable? As long as you can label all the elements in sequence. Okay, label all the elements in sequence. Any idea how to prove this? You show two union first and then you want to use induction. But induction just stop at every end. I want infinity. Huh? Well, okay, cannot. Well, unless you come and do category theory, we can do limit on you. Well, what was the picture inside your mind here? Any picture inside your mind here? You got A1, right? So you should have like something like A1, 1, A1, 2, A1, 3, A1, 4, and then so on, right? Okay. A2, right? Maybe you got A2, 1, A2, 2, A2, 3, A2, 4, and so on. Okay, and then you keep going like that. Hmm? You mean, oh, okay, so you like form a sequence like this, and then you connect here. Is it? How you do? Diagonal thing. So you move here down, move out, and then move down like that. Is it? Okay, let's write a bit more. Let's write one more set. A31, A32, A33, 34. Like that now. A1, 2, straight to A3. Oh, okay, like that. And then after, okay, and then A31, after A31, what do you do? Like that. Oh, and then this one jump to 41. Oh, okay, like that. Okay. Yeah, makes sense. Okay, similar to Q. Okay. Actually, very similar to Q, right? Because Q also like increase in two sides. The numerator part and the denominator. Okay. So you can see that the technique is the same, but it's a different statement here. Okay, or actually you can see Q as a countable union or countable set. Yeah. Yeah, let me think. Countable union, correct. I mean, either is finite, either is infinity, I think. Yeah, depends. So depends where this stop, depend where this stop, and then if it stop, we will take the AI to be empty. You understand what I say? If this AI stop, we will understand it as a empty set. You understand what I say? So okay, so make a remark here. If AI equals to empty for some I greater or equals to n, then the sequence will read like A1, A2, blah, 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 up to A, n minus 1, and then empty, 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 empty. Okay, so you are just union with empty set. Okay, so in this course, often we will do this because we want to have a general way to talk about all the cases. Okay, or not? Okay, ma? Okay, good. So we'll say that a similar proof. Yes, yes, yes. Oh shit. So I should say for all. Say for all. Okay, thank you. Okay. Is it that I such that for all I? Yeah. Never mind. Okay. I think I should say there exists an n. I should say there exists an n here first. Existence is for n, such that for all I after n is empty. Okay. Yeah. Okay. Continue. So today we'll do a lot of counting. Let's go back to kindergarten. Let's take a set of AI, a set of BI. Okay. These two are mutually disjoint set. These two families are families of mutually disjoint set over the same index. Meaning between AIs their intersection is empty. Between BIs their intersection is also empty. Okay. Suppose that we know that AI is equivalent to BI. Okay, for all I in I, then it should be obvious that if you take the union of all AI is also equivalence to the union of all BI. I'll let you think about 2 minutes. So if I have bijection on every set, can I build a bijection on the union or not? Hmm? Okay, if I have a bijection on every AI, can I build a bijection on the union? Okay, so there's a obvious way you can define this bijection. We should try the obvious thing. Okay, in mathematics, always we try the obvious thing first. Okay. Adrian, you want to try? Let me set up first. So let's pull out the only assumption here. Okay, so this is the only assumption you can use here. So we have a bijection between AI and BI for all I. And for all I here. So now we're going to define a bijection F between the two union. What can you do here? So where should the elements go? Use your assumption. The hint is use your assumption. How to use assumption? S go where? Fix. So which I have to use it? Sorry? Which I? Same I with who? Huh? BI? Well, I mean, which, I mean, I mean, this BI will depend on what FI use, right? But this FI depend on X. So if I given an X, how you decide this I? Yes, see where this X in which AI here. Okay, see where this X live in. Is this function well defined? Need to check well defined or not. I think only there's no equivalent class here. Okay, never mind. So we need to check surjectivity and injectivity, right? Bijection. Okay. So is this surjective or not? So take a B in BI for some I. Can you find an X such that fx I equals to B or not? That's a pre-image of B. Can you find it? Assumption, you still got assumption Fi is what? Surjective or bijection. So we can consider the pre-image. Consider the pre-image of B as Fi inverse on B. Okay, this is the pre-image of B. Okay, now Fi on F inverse B obviously is B. Okay, such that F on this element here is B. Right, this is the thing that maps to B. Also, you know where this guy live, right? Where should this guy live? F inverse B. AI. Good. Okay. So actually, we are using this condition. Okay, Fi is a bijection. Okay, how about injectivity? So there's some generality here. You could compare two things coming from a different Fi. Okay. So suppose JK in I and Fj Si equals to Fk S2. Okay, and then we want to show that x1 equals to x2. Okay, could it happen or not? So this j and k, right, can be different or not? If it is in j, this guy live in where? Fj Si. No lah, we map to B already. Bj, right? The other one is Bk, but we said that Bj and Bk are mutually disjoint. So if they have to be the same, J and K have to be the same. Okay. So since Bi's are mutually disjoint, we get J equals to K. Okay, so meaning you have to start with Fj xi equals to Fj x2. But you already reached Fj. What's the property of Fj? It's a bijection. In particular, it is injective. Okay, as Fj is injective, we get that x1 equals to x2. Okay, this course very straightforward. You need to just pull out all the definition out. Okay, then you will get the answer. Okay, and then you will see that, hey, why this assumption so long one need mutually disjoint set because if you're gonna show one of the step you really need the property. Okay, you cannot avoid. Right, so that's why we add the condition in. Okay, you cannot avoid. Okay, or not? Okay, let's continue. If A1, comma AN are countable, then let's take the product of them. Okay, the product set of them. This is also countable. Okay, so you see this kind of statement is depend on n, right? Okay, and then fix for each n, right? So this is where you can use induction, okay, because you have to show for all n. Okay, this kind of statement. Any idea? If n is equals to 1, what happened? It is a tautology. If A1 is countable, then A1 is also countable. Tautology. Okay. Then if A1, A2 are countable, A1 cross A2 is a countable set. It's non-trivial already. So I think you should start from n equals to 2. Think about n equals to 2. How do you show that A1 cross A2 is countable? So if you want to show something is countable, right, make sure you can enumerate them. Okay. Any idea? Sorry? List down the combination. How do you list down? So you want the elements labeling, right? Okay, and then how you list down all the combination? Huh? What do you mean? One by one? Okay. A to 1. Okay, and then A to 2. Okay. Up to A to N. But it doesn't stop right. It's a countable set for both. Huh? Okay. Yes, countable doesn't have to be finite. If both of them are finite, then the product set is also finite because it's just the product of the two cardinality. Yeah. I don't know, so I'm asking him. He haven't finished yet. Right. So you can go this way, right? And then what else you can go? You can get A12 with A21 again. And then like that. Also two ways, two ways infinity. It's like what we did for countable union of countable cell. Do the way we enumerate them. It's okay. But this one is for 2 by 2 case. 3. Can this method generalize or not? Can be induction. Okay. Sure. I think it works. Okay. How about the other way? Let me show you the other way. Okay. So here we say induct the way we prove that Q is enumerable. Okay, that's one more way I can use. So let's say this is the first way. Second way. I also, morally, I'm also using this argument here, but I want to like cut short a bit. Okay, not going through this original method here. So we'll prove by, also prove by induction on N. So let's talk about the general case. Okay, what I do was, I can write AK plus 1 as labeling all the elements. Okay. Then before I get the whole products, right? Let's get this single product first. A1 cross AK and cross one element is enough. Okay, so basically I split the product set, okay, by an element in the last set. Then I think this is easy to see that BI is just as many as the previous product set. Correct or not? Because I just put one extra labeling there. Make sense? Does this make sense or not? This is not one extra thing, this is just I changed name of it. Okay. I changed the name of it. But what is the product of A1 up to AK and then cross the AK plus 1 compared to this BI? How can you form this set from BI or not? What's the difference between these two? Inside here, you got all the other XI. Meaning what? You just take union. You just take union of BI. So this is what? Countable union of countable set. This is what we have proven that it is countable. That's what this set is countable. Okay. Does it make sense? Sense or not? Okay. Yeah, this is a technique. Okay. If you want to use the previous way, also can. The diagonal proof. Okay, so by previous position, it is countable. Okay. Any questions? This part. This part. So what we do was we take the product set of K set and then cross with one element set. One element set. So meaning what? What's the elements inside here looks like? All the AI up to AK, little AI up to AK must cross with one XI. That's all. It's like a constant coming here. So every element in AI and K just attached with one constant element. Obviously, you don't increase the number of elements inside here because you just change the name. All right. Yeah. Okay. 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 Let's see. I think before we take a break, let's prove this. Have you seen this before? The set of n is not equivalent to the interval 0 to 1. Or actually, yeah, okay, make it like this. Okay, it's not equivalent to the interval 0 to 1. Or last time we have shown that this is equivalent to R, right? So it's actually not equivalent to R. Okay. So our proof is we want to show that for any f, okay, going from n to open interval from 0 to 1, f cannot be on 2. Okay, we will use what is called a Cantor diagonalization method. Okay, Cantor diagonalization method. Hey, by the way, did you guys do cardinality in discrete max? To what extent you guys do it? Let's talk about this. Talk about this. You know what? Audience or cameras. Okay. Then we'll go a bit faster. So since you guys heard it before. So let yn equals to fn. We can do this, right? Because our domain is natural number. Okay. And suppose we can write out the decimal expansion for each yn. In this case, we rely that all the number in 0 to from the open interval of 0 to 1, we can write it as decimal expansion. In particular, for real numbers, we can do it. Okay, so what we will do is y1 will get sent to some decimal expansion. So 0 point, let's say y11, y12, y13, and then blah, blah, blah. Maybe terminating, maybe not, maybe yes. Never mind. It's terminate, it's just a zero, a bunch of zero. Okay. So on. So let's write it down like this. Okay, so you notice that when we do this indexing, when we do sequence like particular, at least write down the first two, okay, so that you can guess what happened next. Okay, yeah, because if you say 1, 3, then you should know it's 5, 7, 8, like, yeah, at least two of them. But if it's clear that where you need to put, that's fine. Not that for this f, right, you have to be 1 to 1. Okay, have to be 1 to 1. Because if you want to build bijection, right, you have to be 1 to 1 and surjective. Okay, so we can make sure that it is 1 to 1 by only considering the decimal expansion which do not end in an infinite sequence of 9. Okay, because so let me ask you a question. For example, 0.09999999999. Okay, usually we will equate this with 0.10000. Correct or not? Correct. Is it true? 不对。哇，0这两个号码有差吗？如果有差的，你告诉我一下，蛮重要哎，因为大家讲没差哦0.9999999 squiggly line 是吧？你是讲这样啊？啊，approximately only So you mean there's a difference What's the difference between them? Where's the one? I cannot find the one. Maybe you can develop a theory saying that these two is approximately the same. There's some difference between them. Well, for now, I don't think there's a system can differentiate them. Infinite string of 9. 0.99 and 0.99 and 1 got different, different by 0.01. But if you push the 0.01 all the way to the back, I don't know where it stopped. No, it doesn't stop. It doesn't stop. Keep going on. Okay, so usually we'll equate these two numbers here. Okay or not? Okay, yeah. Yeah, if we don't equate these two numbers, how do you add up 1/3, 1/3, 1/3 equals to 1? You cannot add your 1/3 together. Okay or not? Makes sense. These two is the same. So make sure that when we send the image, right, the image shouldn't land in these two at once. Okay. Okay, so this is some technicality you need to be careful. So we avoid sending n to decimal expansion with infinite strings of 9. Okay, an infinite string of. Okay, so you pick either one of the presentation. Okay, pick either one of them. Okay, don't pick two of them. Otherwise, later you will have a non-one-to-one map. Okay, so we somehow can be a one-to-one map, but we're gonna show you that this F cannot be on 2. Okay, cannot be on 2. So to show that F is not on 2, we will use a diagonalization argument. Actually, it's from Countable diagonalization argument. Okay, so what's the diagonal about it? Okay, where's the diagonal? Okay, where's the diagonal here? So if you look at all the sequence here, we're gonna construct one number that cannot be found in this sequence. Then you are on 2. But then you are not on 2. Okay. So can you, out of all these numbers, can you find a number that is not equal to any of the terms inside the sequence? Huh? Sorry? Huh? So you want to find some diagonal here. And then what you can do with these diagonal? Sorry? You want to change the number. How to change the number? So we're going to build a new number here. Let's say 0.b1, b2, b3, total out to bi. How do we choose it? We choose b1 such that it is not equals to a11. Choose b2 such that it is not equals to a22. Choose b3 such that not equals to a33. Then this number will not be equal to any sequence. Why? It must be differ at the diagonal spot here. With the first number, it differ at a11. With the second number, it differ at a22, and then so on. Does it make sense? Okay. Then you will manage to produce another number that is not in the list of image. Okay. So so there's some technicality here. Well, what's the technicality here? So how do we do this? So we can do this systematically. How to do it systematically? We just pick Bn to be ANN plus 1 mod 9. Okay, add one more up. How to pick a different one? Because 1 to 9, right, you got 8 choices to do. Okay? 10, you got 0 to pick, right? 0 to 9 digit. You got 10 choices, right? Okay, then you cannot pick one of the choice. You got 9 choices. Okay, out of these 9 choices, which one you want to pick? So we just add by 1. Okay, let's say A11 is 1. Then you just pick B1 to be 2. And then if A33 is 9, it's 3, 9. 9 plus 1 is 10. Huh? 9 plus 1 is 10. 10 mod 9 is 1. So you bring it to 1. Just add 1 up. Okay, just add 1 up. Carry on up. Okay. So that the decimal expansion for Z doesn't end in a infinite sequence of 9, infinite string of 9. Okay. Actually, there's another proof using a completeness of R. I won't present here. I put inside the lecture notes. Then you can use a nested interval, like what we do in MA. Yeah. Mm. Mm. Okay. You get 8 plus 1 is 9. You get 0. Hey, wait. Yeah, you get 0. Yeah, you get 0. You get 0, yeah. Yeah, you get 0. Yeah. So 0 is different from where you start. You start at 8, right? So 0 and 8 is different, right? Yeah, okay. Ah, ah, okay. Okay, so the corollary here is what you need to remember is n is not equivalent to r. Okay. Otherwise, so if you want to put some proof here, otherwise, you have n equivalent to r and then r equivalent to the open interval we shown last time. And then this is a contradiction to what we proved just now. Okay, which is a contradiction. Okay, so before we take a break here, since we have discovered something that's different from natural number here, we will say that a set is uncountable. Okay, uncountable if it is not countable. Okay, and then we say that if a set X is equivalent to an uncountable set R, we will say that it has a cardinality C. Okay, it has a cardinality C. This C will represent something called continuum. Okay, later we'll talk about continuum hypothesis. Okay. Okay, any question before we break? Okay, let's break until 11:04.哎，思颖呢？思颖在哪里啊？还在睡觉？他昨天讲不舒服哦。啊？什么？他讲吗？你讲吗？你讲吗？他讲什么？他讲什么？啊，他每天不舒服。哎，读书就头痛是不是？有点像我弟弟。啊？
哎呀，你为什么发来让我可以递过去？没有，别。开始啊，开始了，就要
猜出来？
哦，这开始了。
对咯。什么歌来的？这样都看。这个应该是可以。去问人， 问人
你那个红
啊？哦，OK OK OK。 Hey Rachel, your house got blackboard? 他没有 house got blackboard one.
哇，你还要
But you rent one, you can make a blackboard then.
Cause you
Then you left the blackboard to them. You bring it back later.
like physics friends that they'll be younger than me. So it's their problem. but after that, 如果没有 like 数学物理系 then just donate to school. Yeah, but that's 4 years later.
不是他那个版主不要跟你们做还是like 你们就做吧，
就做了，
没有问他，不用问他。
只不要撞动还是什么就 OK 了。
你有装还是没有装？没有装动那你那个请他弄上去了。
But
是咩？是咩？那个照片还有在吗？我没有注意到哎。谁的 IG？看下。钉哎，
你买白发？
哎没有了，不见了。等你还差一个香在那边了，拜拜。What 味道哦？那个是那种人家放在盒子里面的那种，
是这种。
印度人，你要有那个 Raman 都这样摆。可是那个粉这样多不会来
在宝格丽，
在旁边。我看到你有 modem 在上面哦，你 modem 不会知道很多粉的。
就是没有那个模的要缝在一起啊，
其实神吧。
What do you mean？
要买啊。
有啊，有一个 website 有啊。
Yeah，那个 website 就比较贵了。
比较贵咩
Yeah，like for 那个 size 会来500。
？Then 你买多少
300。
你去哪里
在一直在 Shopee 找。
好。
Yeah，对，原本是找淘宝，反正过来。
他从哪里寄过来？
哦，有一
从 IOI 寄过来。IOI 卖的，谁卖的？Shopee 是谁买？
就有一个
马来公司。
那是有 stand。
是有 stand 啊，but 我本来是要装的 package，他叫我便宜，他讲可以装，你装了让你便宜。
那还没得看。
我也是可以买他们。
有一个黑的美的，
对啊。
会怎样3分3A？就是球很超大。
他 story 有多少人在这边？
他后来没有。
是什么？
有 story。
本来现在手艺。
This one go white one。
Yeah，我只有一找单，
不容易找。
对，就找个外国在手艺之类的。
把这个他会帮你留好的嘛？这间店。
你觉得他？
要去买个那个。
100多。
好，等下追不到丢到手怎么办？
要看，就200多块。
OK。哎，其实他从天来啊，早知道我叫你帮我。他送过来还要200块了。
能收我能收
啊？
钱收。
是啊。
老板都钱。
OK。
老板你
他先。
对吧？
可以的。
Yeah, but from the
还慢慢的变大，
so
然后有那变了，变大，
你会尝试，可以加费了，一个这边 OK，
帮他来吧。你要讲好，我这里玩我这里对吧？
基本上也是就是它这个证明没有。
没有，因为
你还有另外的
然后再真的然后基本就是我非常比较 feel 的对。
对，我电梯跟我说。这个计划只有现在跟很多的你，通过一个地图来，我们是有对台的，
我们可以这种
我跟你讲休息要几点
11:05，
零五啊
04:05，
零四啊应该是零四吧因为我对5比较敏感
因为不是5秒米，对啊5秒秒真的，
所以我就会忘记我会记得5啊如果是准5啊这样
所以讲5就比较好啊，讲04就通过这来。
因为我怕等下塞时间希望今天我们可以结束掉这个卡丁卡议题
这个
这个还是那个 4吧，开玩笑，但是这个还是他们3个项的那个，
好噻
他可能会来
哦没有因为那时候我为了方便不是你有看的话 lecture 5其实就短短吧因为我把这个卡丁 ID 全部挤在一起让他们比较容易翻如果我断掉的话它就只有1-2面是那个 matrix 所以我把它拉去前面差不多了
其实是一样的。
差不多了如果拉到6就会有一点点迟 OK hello let's start Okay, hopefully we can finish cardinality today. And then this week we'll start metric space. And then I think it will be very familiar for those who are taking MA2 concurrently with general topology. Okay, so let's define to each set. Okay, we will associate a symbol. Okay, a symbol. This symbol could be number, could be alphabet. Okay, but we just call it symbol. Okay, and then the symbol is called cardinal number or cardinality. Okay, so now we have formally defined what's the cardinality of a set. So it's just a symbol. Okay, so if I say you did not a symbol, right? So you should ask, how should we assign this symbol? What's the rule to assign the symbol? Okay, so before telling you a symbol, I'll say that 2 cardinal number is the same if and only if x is equivalent to t. Okay, so we use bijection to see this symbol. So for example, if f is empty, we will just say that the cardinal of this set is 0. Okay, nothing inside there. Okay, very intuitive. Huh? If the set is equal, okay, equal. I cannot say equal, huh? Okay, so I just put bijection. Bijection to a set A1 up to AN. Then we will say that the cardinal of this number is n. Okay, makes sense? Okay, bijection to a set of n elements, then the cardinality is n. And we got few others bijection, right? So we have proven bijection to n is the enumerable. Okay, so we'll say we'll put d for it. But sometimes in the literature, you'll see omega. Okay, also some literature put L left 0. Okay, I left 0. And if S is in bijection with R, just now we know that it's not equivalent to N, right? So we should give it a new symbol. So just now we gave it C, okay? Or some technical point here, sometimes some of them refer it to LF1. So meaning is the next infinity. Okay, but there's some technicality involved here, but we don't want to explore it. So this is cardinal number, okay? So if you go to other courses that talk more about foundation of max, they will have ordinal number, okay? Yeah, to govern even more infinity. Okay, so there are more infinity than this. Okay, so now we just stay with the numerable and this cardinality C. Okay. Next, we were going to compare these cardinal. These are simple symbol. These are just symbol. So in our mind, right, we don't know what is the relation between 0, 1, 2, 3, 4, up to n. These are just symbol. Okay, symbol only. I just ask you to count. You don't know whether 4 is greater than 5 or 5 is greater than you don't know whether 5 is greater than 4 or 6 greater than 4 or any other things. So we're going to define a new ordering here. Okay. You just see them as a symbol. It's a symbol. So suppose S and T are two sets. Okay. We will write the two symbol. Okay. Cardinality of X less than or equal to cardinality of T if S is in bijection with some subset in T. Okay, we use bijection on subset to define less than or equal sign. Okay, you need to build a map. Okay, so whenever you see this cardinality of X is less than cardinality of T, you need to build a bijection from S to some subset in T. Okay, for some subset M. And then if we have the cardinality of X less than cardinality of T, and this two cardinality is different, so the symbol is different, then we will write that the cardinality of X is strictly less than cardinality of T. Okay, so we are defining a new ordering on symbol. Okay, so first proposition we will get is 0 strictly less than 1, strictly less than 2, strictly less than 3, strictly less than any finite number, and then less than B, less than C. Okay. So we will cover something that you know in real numbers. Well, yeah. Okay. We will recover something you know in real numbers. Okay or not? Using this definition here. Okay. So meaning these symbols are realized by some set, which is empty for first case. Second case, set containing one element, containing two elements, three elements, and then set as many as the elements inside the set as many as the element in natural number, and then same as real number. Okay. So let's quickly see this. So in this case here, we just consider some general set. So set containing one element, and I think we need to put empty set also. Okay, to realize these symbols. Okay, so we realize the symbols here. Okay. Obviously, we don't want this AI to be the same, where AIs are different. Okay, if they are the same, we will have a degenerate set. Okay, we don't consider multi-set in this class. Okay, so let me warn you here. Warning. No multi-set here. Okay, so for example, set containing 1, 1 is just equal to the set containing 1. Okay. Maybe if you go to combinatorics, they consider multi-set. They need to count different one. Okay. But in our case, we don't consider multi-set. Those are called multi-set. Okay, where you can repeat your element. All right. One inequality is very obvious, right? So obviously, what is obvious? Obviously, we have 0 less than or equals to 1, less than or equals to 2, less than or equals to 3, less than or equals to D, less than or equals to C, right? How to see this? What's the definition? Less than or equal to? You just need to have an injection. Okay. So you can inject or not? Can you make an injection between this set? Inject, inject, inject. Okay. In fact, there are few ways to do injection. If you look at, for example, the first map here, how do you inject a set containing A1 to a set containing A1 and A2? Actually, there are more than one way to inject it. Function, how to define function? So you just need to tell me where the A1 have to go, right? A1 can go where? Either it can go to A1 or either it can go to A2. Actually, there are two ways of injection here. Okay or not? But in the number system, 1 is only less than 2. That's all. But in this set theoretical way to define less than, you have two ways. Okay, there are two ways 1 can sit inside 2. Correct or not? 2 is 1 plus 1, right? So which one you are talking about? Okay, does it make sense? Okay, so there are actually more ways to do this injection. Okay, so these are do through injection set. So now we are left to show that they are not equal. All of them are not equal. Okay, so obviously some is obvious. Not that for any n in n is not equals to d. Okay, because last time we have shown that n is not finite. Okay, so we can slowly reduce one of the inclusion. Okay, so inequality, sorry, not inclusion, inequality. So n is strictly less than d. What else? Just now we proved that n is not equivalent to r. Okay, so we also can throw away the inequality between d and c to make it strict. Okay. And then how about the rest? The finite guys, how to show? The finite guy, how to show? Obvious 来讲一下多 obvious. If it's obvious, then it's easy to say. 来讲一下，讲 obvious. Oh, so you mean you can find an element in the larger set that's not in the smaller set? Yeah. Okay, you can use that. Okay, so the fact that 1 is not equal to 2, 2 is not equal to 3, and so on, actually can prove by induction. So basically, you start by the showing 0 is not equal to 1. Okay. So here is empty set, right? Here is set containing 1 element. So empty set is nothing. If 0 is equal to 1, what happens? Everything will collapse. Nothing already. You say got something, but something is nothing. So you got nothing. I don't know. So the world will collapse if 1 equal to 0. Okay. But if you go further in logic, sometimes you need this absurdity to define some infinity. Yeah. I mean the largest infinity, I think they call it 1 equals 0. if I'm not wrong. You can go and find it if you're interested. Yeah, the largest infinity actually is nothing. They call it nothing, I don't know. Yeah. These people are doing logic stuff. Okay. All right. So what I want you to know from this proposition is we recover the ordering on the natural number, okay, including 0. Okay, and we can compare natural number with D and C. And actually, this is a chain, right? Okay, they are totally ordered. This is a chain. Okay, so corollary for any infinite set S, the cardinality of S should be greater or equal to D. Okay, should be greater or equal to D. Why? Just now we have proved a statement that if S is infinite, it will contain a denumerable subset. Okay, if S is infinite, X contain a denumerable subset. Okay, denumerable subset. So there's a denumerable subset inject into S. Okay, inject into S. If you want me to write out in full, we can see that then P will inject to S. So by definition, the cardinality of X is greater or equals to the cardinality of P, which is equals to D. Okay or not? Okay, so we're just trying to turn the fact that we've proven before into the cardinal symbol. Okay, cardinal symbol. And then proposition, if A is infinite just not finite, and B a countable set, then if you combine A and B together, match them together, how big is it? What do you think? Infinite is not finite. Not finite, what could happen? You could be denumerable, could be uncountable. Okay. And then if you combine with a countable set, what are the countable set? Either finite or either denumerable. Okay. What's the effect of joining them together? Would it increase or not? I think cannot decrease, right? For sure, you're adding something cannot decrease. Would it increase or not? If it increase, how much it increase? Or you want to write down something like this? I think I haven't teach you plus, right? There's no addition between those symbols. So actually, it is just as big as A. Although you already add something in, it's just as big as A. So meaning what? There's a lot of room that you can play with this infinity, you know. There's a room to play with this infinity. Yeah. Okay. So how on earth we're gonna think about this? You add something, but you didn't increase the cardinal. Okay. And then adding something, this is just countable. I didn't say any addition is the same. This is just countable. So you need to make use of this countability here. Okay, you need to make use of this countability here. Okay, so what can we do here? Let's do it. Let's see what's the technique we can use here. So since A is infinite, by previous theorem, we can find that we can find a denumerable subset here. Okay, we can find a denumerable subset. Here we can find a denumerable subset. Well, since B is countable, what we could do is we get rid of any A elements in B first. Okay, it should be countable also. Okay, because countable is finite and denumerable, right? So if you throw infinitely many of them, it could be still countable, or it could go to finite, but still countable. Okay. Yeah. Or one way to think about countable is you can label them in sequence. If you throw the elements away, you still can label them in sequence, right? Because you are just taking subsequence. Okay, after removing. Well, so in this case here, there's a trick here. Then it follows that A1 union this countable set should be countable. Okay, so let's write down in the cardinal form. So the cardinality of A1 union B take away A is D. So in this case here, we have two denumerable set here. So we can say that actually A1 is as many as A1 union with B take away A. But we're going to deduce for A union B. So how can we go back to A and A union B? How do we go back? How do we go back to A and A union B? So we are trying to use this bijection to build a bijection between A and A union B. Is there any way to get back to A and A union B? This bijection here. We're gonna use what we learned just now. We're gonna use what we learned just now. So I'm gonna union with this A take away A1 to this two set here. And then I still have a bijection. Can you remember which proposition we are using here? Just now we got a proposition, right? If we have a bijection between AIs and BI, if they are mutually disjoint, then we can combine all the bijection together. So in this case here, can you see that A take away A1 is disjoint with A1? Okay. And then A take away A1 is disjoint with A1 union B take away A. These two are disjoint. Because you take away A, right? A1 already. So A1 on the other side. And then A on one side, but you take away A already. Okay. So, okay, so and then the bijection between A take away A1 is obvious, right? Is the identity map, right? So this bijection is obvious, right? Is the identity map. And then this bijection, let's call this F, huh? This is F. Okay, so we combine these two bijection together. So by previous theorem or proposition, we get the following bijection. Okay, we get a following bijection. But the magic is here. What is A take away A1 union A1 啊？多此一举哦。拿掉 A1 又把 A1 放回来。What do you get? A. Okay, how about the other side? You take away A1, you put A1 back again. You from B you take away A, but you put A back again. What do you get? A union B. So this is a bijection between A and A union B. Okay. Okay. So we are done. Okay, no? Yeah, so this is a little trick you can use here. But this little trick is quite useful. It's quite useful. For example, we can see that the irrational number are as many as the real numbers. Hey, did we prove this in MA? Did we do this in MA or not? No, right? No or yes? Forgot. No. Don't know, huh? Okay. But how to show this in this case here? So what is rational number here? Okay, rational number is as big as rational number plus rational number because rational number is countable. Okay, last time we showed that it is countable, denumerable in particular. But what is A? What is R slash rational union rational? This is real number. Okay. But real number, the cardinality of real number is C. Okay, no. So there are as many irrational and real numbers. So the max you do only use rational, you know. How many irrational you know? Pi, E, what else? Square root 2, all the roots. There's a lot more irrational than rational. Okay? There are a lot more of it. Okay, let's continue. Suppose A is non-empty. Suppose A is non-empty. Then for any set B, we could find a map, an onto map from B to A, if and only if the cardinality of A is less than or equal to the cardinality. Okay, so how to think about this? Let's write down what's on the both sides. Okay, on both sides, what does it mean? So you have a set A, set A. How about use the other color? Blue. You have set A, okay. Then you have set B. Okay, and then A is not empty, so there's something inside here. It says that if you can inject B to A, if and only if, what happened? A can be injected into B. Okay, meaning A can sit inside B here. Okay, this is what it means. If you want to build a surjection here, meaning this map has three images inside B, if and only if you can put your A inside B. 合理吗？你觉得合理吗？ You need to map to everything inside A. Meaning you can have an injection inside B already. You can see inside B, 对吗？ I mean, well, 你要 suggest 你讲 suggest Have you think of a problem here? If you only got 3 elements, can you subject to 4 element set or not? Can or not? Can subject? 这样可以啊？可以这样做啊 ？Why not？正月，做不可以 ？Yeah, this is not a function. Okay, so if it is onto, right, for sure you should have at least as many items inside your codomain. But in this way, you can try to make a injection back. This is the idea. 合理吗？ Make sense? Okay. Okay. Let's do this proof because this proof is a bit technical. I think we should see it once. Yeah, let's do this proof here. Okay, let's go forward. So go forward means what? If you want to, if you suppose you have a G is onto, okay, you want to build this injection here, F. What do you think? What's the injection you can do here? This is your assignment question. Because you want to go backward, there's one way you can go backward, right? This is an onto map. So how you go backward? Assignment question, right inverse. Yes. Okay. So by action of choice, we can define a right inverse function such that g of fx, so here is g, here is f, g of fx equals to x for all x in A. Okay. Is this function one-to-one or not? Did I ask you to prove? Did I ask you to prove? If GF identity and then F have to be injective. 有吗？有这个 assignment 里面吗？没有这个 assignment 啊？有啊，有啊，其中一题也是。Okay, then F from A to B is 1-to-1. Okay, it's 1-to-1. Okay, how about the other direction? Or the other direction? So the other direction will suppose that the cardinality of A is less than or equal to B. So this means what? Okay, this is not the number less than equal. I want to remind you 请忘记掉你以前的那个小于等于你现在要记的是有一个 injection. Okay, what you need to remember is there's an injection now. Okay, so what's the injection here? There's an injection from A to B. Okay? A to B. So now you're going to define an onto map. So how to define an onto map using this F map? So now you're going to define a G from B to A. Okay, using this F here. So you need to tell me where these B have to go. Or let's say Y. You see, you only have a single assumption here. So try and use it. Okay, so what can you do? If I give you a Y here, how can you play around with F? What is the element you can send to? Obviously, you need to send to something in A, but how do you decide this X here using F? Can you decide? If fx equals to y. Okay. Does this work or not? Let's check. So when we define something, right, we check. We didn't say that what we define must be correct. So we just check. Okay, does it workable or not? So meaning, is this S unique or not? Because you want to define a function, right? For every y. Is this X unique or not? Is the pre-image of y under F unique or not? Because F is a one-to-one. Okay. But the problem is, if this y is not in the image of F, because this map might not be onto one. Maybe there's some B it doesn't map to one. So for those y it doesn't map to, what to do? Huh? Just sends to something, anything. Doesn't matter, because we just want that this map is onto. So if there's no such, okay. Okay. Why is it onto? By the way, why this map is onto? We haven't checked yet. Why is it onto? Why is it onto? Because A is because F is defined on A. So your F must have value for every A one. Yeah. Okay. I will say that G is clearly onto because F is defined on A. Okay. Does that make sense? So meaning if I give you anything inside A, how to find your Y? Give to F. F will tell you where it should go. Then you can find the pre-image already. Does that make sense? Okay. Because F is defined on everything on A. So this guy here is not very important. Because our codomain is quite small compared to B. Okay. Then we will have a series of theorem here. So we are really building a number system out of this cardinal number. So that's why we call it a cardinal number. Okay, so we try to differentiate this cardinality to the usual number that you know. We call it a cardinal number. Why is it a number? We'll prove to you that it has a number property here. Okay, for example, the cardinality of A should be less than or equal to the cardinality of A. Obvious or not? What's the injection you can pick here? Identity map. Okay. And then well, let's not give you the second one first. Give you the third one first. If the cardinal of A less than cardinal of B, and the cardinal of B is less than or equal to cardinal of C, it will also have the transitivity property here. Transitive or not? Meaning composition of injection is still an injection. Okay. And then last one, either the cardinality of A is less than or equal to cardinal of B, or the cardinality of B is less than or equal to cardinality of A. Okay. I don't want to present this proof, but this proof here actually uses Zorn's lemma actually quite strong, this result here. Okay. To say that two of the number must be comparable to each other actually quite strong. Okay, you need Zorn's lemma here. I don't want to present this proof. And the other one that I doesn't want to present is called the Schroeder-Bernstein theorem. This statement seems easy. What is this statement here? If you know that you have an injection from A to B, and you have an injection from B to A, actually they have same amount of element here. Turns out to be quite hard to prove. Anti-symmetric. Okay, it's a quite long proof here, but quite interesting. I won't prove here also. I will left the proof inside the lecture notes. Okay. Basically, it splits your elements into three parts. One part coming from the first injection, the other part coming from the other injection. And then you need to discuss if they are not in this injection, where should they go? It turns out that you can make it a bijection. Quite interesting here. The proof is quite constructive. So easy one is easy, hard one is hard. So let's finish this here. Let's go to the next one. So this is the thing that we want to deduce here, which is the trichotomy law. Okay, actually this cardinal follows trichotomy law. Okay, so if given two cardinal numbers, right, either they are strictly less than each other or they are equal to each other. So this match up with our understanding with real numbers. Okay, so that's why we call these cardinal numbers. Okay, so will we do this proof? Okay, so maybe this proof is a very standard proof. I think this one can give to first year. Without knowing what's the cardinal, you can prove this. So let's see. So either these two numbers is the same. If they are the same, we are done. If they are not the same, then previous theorem tells you that either the cardinality of A is less than or equal to the cardinality of B, or the cardinality of B is less than the cardinality of A. But since they are not equal, right, it is only the case that one of them is strictly less than the other. Yeah. So this proof doesn't involve what you need to know about cardinal. Without knowing cardinality, you should be able to prove this. Okay, so that's why I said this can be given to first year. Okay, without any understanding of cardinality, I just give you the previous theorem and you can do already. Okay. So I still got 5 minutes. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's see how it goes. Although I don't have time, but I still want to do this detour. I need to advertise category theory here. So what we have done here is called the finite set categorify the natural number. Okay. So on top of this number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We have a set that realize this number. We take a set, and then we put the cardinal symbol on it. It will reduce to natural number. Okay. So what do I mean by categorify here? So obviously I need to define what's a category for you. So let's define a category. Let's call it script X or finite set. I think we will end here. So let's finish this. So a category of a finite set just consists of two data here. Well, one thing is called objects. Okay, objects is the finite set. And two is morphism. So the morphism here we consider injection. Okay, just now we just consider injection. Okay, so here what we do was given you an object in this category, we can put the cardinal symbol on it, and then you will land in the natural number. Okay, so what's nice about this? The structure of n can be lifted to this category here. Okay, So in natural number, right, you just know that, oh, 1 less than 2, 1 less than 3, 1 less than 4, that's all. But in this category, right, what happens here? If you know 1 less than 2, right, it could imply 2 cases, you know. Okay, there are 2 cases here. 2 cases is what we discussed just now. How do you inject a set of 1 elements inside a set of 2 elements here? How do you inject it? Okay, so either there are 2 ways of injection here. X1 can go to X1, or second map is S1 go to S2. So these are 2 perfectly good injection you can take. Okay, F1 not equal to F2. Okay, so out of this symbol here, 1 less than 2, we could have 2 possibilities. So we have more things to consider inside this category here. More structure. Cannot. We have more structure. But here, just less than. Okay. So this is what we call categorification. Okay, so you have seen some form of categorification. Okay, this will not be in your exam, no need to worry. No need to worry. This is just something extra I want to tell you. Okay, actually this kind of structure you can see in various fields in mathematics. As long as you have some objects and then between objects you have maps, then you can form category already. And then we can do categorification. One kind of this is what we call decategorification. We make it a non-category here. So one form of decategorification is just to count how many things inside there. Okay. There are more ways to count things. Maybe we will say that this group of things have different grading. And then we can build a polynomial out of that. Okay. And then this is how we get not invariant. John's polynomials. Yeah. Conway polynomials. So all the coefficients in front of these monomial are counting some object. In particular, we will count the dimension of vector space or dimension of modules. Okay. Yes. How do you define bigger? More structure. I'll say more structure. More structure. More structure actually more restrictive, you know. More restriction you can put. Yeah, categorization make it more structure. Something that we cannot solve in a lower dimensional thingy, we can solve it in category. Because in category have more structure. Okay, so that's why the research frontier now is in category theory. Not just pure maths, computer science also work in category theory already. Yeah, computer science. Yeah. Cannot run away from category theory already. Maybe in future, these are the things that you need your children need to study already. Category theory. Your children. Because our maths foundation move further already. Move up already. Our foundation is in category now. Okay, previously it's just set. Right now it's category. Okay. By the way, I want to remind you, the deadline of assignment is quite important. So if you miss the deadline, 1 day penalty 3%. Okay, so please keep the deadline. Tomorrow we can discuss about assignment 2 deadline again. Okay. So assignment 1, the deadline is 10. So make sure you hand it in soon for those who haven't done it. Okay, so see you tomorrow.